Alright, this video is going to show some examples of simplifying radicals, a few different kinds. Some of these questions are from various homeworks that we worked on last week, so you should go through these as needed to refresh your memory about different strategies we have for simplifying radicals. This first problem, we've got the cube root of 10 over the cube root of 625, and I know that this one looks tough because we've got a big number as the radicand in the denominator of the fraction. Whenever I see that, the strategy that I'm going to think of first is trying to simplify that radicand or that radical before I look at rationalizing by creating a fancy one. So what I'm doing at this point, I'm using a little thought bubble and a big thought bubble, and I want to simplify the cube root of 625 as much as I can before I move on. So I'm asking myself, we know we've got a bunch of perfect cube numbers. This number is positive, so I'm thinking about the positive versions of the perfect cubes. I have 0, 1, 8, 27, 64. That's the first few. After 64, so 4 times 4 times 4 is 64. The next one is 125. And it turns out that this one's going to be useful to me because 125 is a factor of 625. So if I do my factor cake and I divide 625 by 125, I get 5. 5 times 125 is 625. So I'm going to, in my thought bubble, I'm going to rewrite the cube root of 625 as the product of 125 times 5. From there, I'm going to break it apart, so I'm going to have the cube root of 125 times the cube root of 5, and the cube root of 125 is just the number 5, so I have 5 times the cube root of 5, and this here is equivalent to this here. So from here I'm going to rewrite my original problem as the cube root of 10 over 5 times the cube root of 5. It's still the same. I haven't changed anything moving from this step to this step. The only thing I've done is rewritten this in a little bit simpler way. From here, the next thing, I still want to keep my number small. I could start moving straight to finding a fancy one if I wanted to, but one thing that I notice is I've got two radicals that have the same index. They both have an index of 3, and we've got division in between them in the form of this fraction bar. So before I do anything else, I'm actually going to simplify that because I like to keep the number small. So I'm going to change this problem. I'm going to break apart this part from the radicals, and I'm going to make it 1/5 times the cube root, and I'm going to put the whole second half together, the cube root of 10 over 5 like this. Notice the whole fraction 10 over 5 is part of the cube root. Now this is useful to me because 10 over 5, I know, is just 2. So I have 1 over 5 times the cube root of 2. And then if I think about this still as a fraction to put everything together, that would be the cube root of 2 over 1. And if I multiply across the top, 1 times the cube root of 2 is just the cube root of 2. And 5 times 1 is just a plain old regular 5. So I was able to avoid working with big numbers at every step of the way except for this initial step where I was simplifying the cube root of 65 up here in my thought bubble. The next problem that we're going to look at is 8 times the cube root of 384. And this is just a simplifying one. We don't have a denominator with a radical in it, so we don't have to worry about rationalizing. And again, I've got 384, which is a big number, and it's positive, so I'm automatically thinking about those positive perfect cubes, 0, 1, 8, 27, 64, 125, and so on. And I want to start breaking 384 down using the factor cake. So I'm going to put 384 over here, and I'm not sure which one goes into 384 evenly. But it looks like I could probably divide 384 by 8. So I'm going to start there with my factor cake. 8 goes into 38 4 times. 8 times 4 is 32. 8 minus 2 is 6. 3 minus 3 is 0. And if I bring down my 4, 8 goes into 64 8 times. So it does divide evenly. And I'm going to need to continue on building my factor cake, because if I look at 48 here, I know this time that that is divisible by 8. So I'm going to want to continue on with my factor cake, building another tier. 8 goes into 48 6 times. So I'm looking at the numbers that are the decorations on the cake, 8 times 8 times 6, to create my 324 number. And I'm going to rewrite that 384 using those multiples. So we have 8 times the cube root instead of 384. I'm just going to rewrite my decorations on my cake. And then I'm going to bust everything apart. So my 8 stays the same. And then I have the cube root of 8 times the cube root of 8 times the cube root of 6. My 8, again, stays the same. And now I know the cube root of 8 is really just the number 2. And I've got 2 of those. And then I still have the cube root of 6. There is no perfect cube factor of 6, so I can't simplify that any further. And then I'm just going to multiply across. So 8 times 2 is 16. 16 times 2 is 32. So I have 32 times the cube root of 6. Okay, the next problem we're going to do, this is a relatively easy one, but I just want to show you one very straightforward example of rationalizing. This problem has 4 over the square root of 3. It's a square root, so I'm aiming, when I multiply by my fancy 1, I want my fancy 1 to give me a perfect square underneath the radical right here. I'll draw a square so that I know I'm looking for a perfect square. So if I have 3 and I want to make a perfect square, the next perfect square that I can think of is going to be 9. So I'm going to use the fancy one, 3 over 3. Remember, this is a fancy one because the numerator and denominator have the same number. So I'm not changing the problem any when I do that. 3 times 3 again is 9, so I have the square root of 9 in the denominator, and I have 4 times the square root of 3 in the numerator. From here, I know that the square root of 9, this bottom part here, is just equal to a plain 3. So I have 4 times the square root of 3 over 3. And that is as simple as I can go. The other thing I would want to check here, I would want to check to make sure that this can't be simplified any further, and I would want to check to make sure that the plain number part is not a fraction that can be simplified further. Okay, this next one is going to be basically another one that involves rationalizing, to show you a slightly harder example. If I have the square root of 4 over 4 times the square root of 6, I've got lots of first steps that I could take here. I could move straight to the fancy one and find a fancy one that's going to create a perfect square. But using our principle where we want to try and keep the number small, I'm also going to think about the fact that I have a square root on top and a square root on the bottom. And I can simplify across that vinculum, that fraction bar, before I get started. So I'm actually going to bust this up like this, where we have 1/4 times the square root of 4 over 6, like this, so that I can simplify. I know that 4 over 6 is equal to 2/3. So I have the square root of 2/3 instead of 4 over 6. And now I'm kind of going to go backwards a little bit to make it look more like this again, so that I can work on my fancy one. So on the top I have 1 times the square root of 2, that's the square root of 2. On the bottom I have 4 times the square root of 3. Now I'm not finished because I still have this radical in the denominator, but now I'm working with smaller numbers than I would have had originally. So I'm going to multiply times the square root of 3 over the square root of 3. That's the fancy one that I'm going to use. And from there, I've got, across the top, I have the square root of 2 times the square root of 3. That's going to give me the square root of 2 times 3 like this. And across the bottom I have 4 times the square root of 3 times 3. Simplifying, we get the square root of 6 over 4 times the square root of 9. But we know what this is equal to. So I really have the square root of 6 over 4 times 3. And we know that 4 times 3 is just 12. So this is the fully simplified version of things. Okay, this is the last example that I'm going to do. We're going to do negative 3 times the square root of 5 plus 2 times the square root of 54 plus 2 times the square root of 45. In order to combine these three, to add these three together, they have to have the same radicand. In other words, the same number underneath the radical. Right now, they all have different numbers. So I'm going to try and see if I can make them be the same. So I'm going to get a different colored pen so I don't get confused. I need to do a little bit of scratch work here. So I'm going to do a thought bubble with this expression, and then I'll eventually need to do a thought bubble with this expression. I don't need a thought bubble for the first one because the square root of 5 is simplified as far as it can go. So right now I'm going to work on 2 times the square root of 54 to simplify that part. If I'm thinking of my factors of 54, 9 times 6 is 54, so I'm going to rewrite this as 2 times the square root of 9 times the square root of 6. The square root of 9 is equal to 3, so I have 2 times 3 times the square root of 6. That's just 6 times the square root of 6. If I move over to the second thought bubble, I've got 2 times the square root of 45. 45 is 9 times 5. So I have 2 times the square root of 9 times the square root of 5. But the square root of 9 is again just 3. So I have 2 times 3 times the square root of 5. 2 times 3 is 6. So that gives me 6 times the square root of 5. So, putting this all together, the first term, negative 3 times the square root of 5 stays exactly the same. The middle term, instead of 2 times the square root of 54, I'm going to rewrite it using my thought bubble. So plus 6 times the square root of 6. That's still equal to 2 times the square root of 54, but it looks different. And my third term, I'm going to rewrite as 6 times the square root of 5. Again, still equal to this original part, but it looks different. Once I do that, I'm looking and I see that I have 2 terms that are alike, and I have 1 term that's different. The 1 term that's different cannot be combined with the other 2. It's going to stay as 6 times the square root of 6. And if I combine these other two, negative 3 times the square root of 5 plus 6 times the square root of 5 is going to give me 3 times the square root of 5. And that is as simple as that one gets.